All right, topic 4.5 is actually starting to solve problems using related rates. And we have practiced setting up equations that related how the variables were changing in a situation. And so today we're going to solve the whole problem. And the problems we're going to deal with today are going to be round things and rectangular things. All right, so the first step is to write down every given information or quantity, even what you're looking for, and make a sketch. All right, so for example 1, the radius of a circle is increasing at a rate of 3 centimeters per second. How fast is the area of the circle changing when the radius is 5 centimeters long? And looking at that, it can feel really overwhelming. So we're just going to write down what we're given. So it starts off, the radius of the circle is increasing. So we want to change that to calculus language. And so for radius, we usually use r. And so a change is dr dt. So that represents how a radius is changing. And since it's increasing, it's going to equal a positive 3 centimeters per second. Okay. Now what we want to find is how fast the area is changing. So the change in area is going to be dA dt when the radius is 5 centimeters long. All right, so just getting that written down is a huge step. All right, step 2 is what we've actually practiced the most, so hopefully you'll be okay. We're going to determine the equation needed to solve for your unknown quantity. So we're talking about radius and area of a circle. So that's going to be the area of a circle equation or formula. Area equals pi r squared. Okay, step 3. Take the derivative implicitly, not forgetting to multiply by dv dt or dA dt or dL dt, depending on what the variable is, for every single variable. So when we differentiate this, we're differentiating it with respect to time. So none of these variables are time. So when we find the derivative of a with respect to time, it's dA dt, right? Pi is a constant. So we'll find the derivative of pi r squared, so that's 2 pi r, and then we're going to multiply that by dr dt. Okay, so on this circle, I should have talked about that, but on this circle, the area is changing and the radius is changing. So we don't have any constants going on except for pi. All right, then step 4, plug in all your given information or quantities and solve. All right, so we are finding dA dt. So that is what is over on the left. All right, so I'm going to leave that, dA dt. And then r is going to be 5. And then dr dt is 3. Now we could put the units with it if we wanted to. So it's really 5 centimeters times 3 centimeters per second. That might help you when you're thinking about units. But I would multiply those together and get 30 pi. All right, and we are multiplying centimeters by centimeters per second, so that gives you square centimeters per second. Now what I usually do is not really worry about the units as I go. I usually just do the units at the end. So I know area is always a square quantity, like square inches, square feet, square centimeters. And so a change in area is going to be a squared quantity per time. So in this case, square centimeters per second. All right, so let's look at another one. For example 2, a water tank is in the shape of a cylinder with radius 5 meters. Water leaks out of the tank at a rate of 0.2 of cubic meters per minute. When the water in the tank is 8 feet deep, how fast is the water level falling? All right, so let's talk about this water tank for a second. this one I may need a picture. The circle, I was okay. I can kind of visualize that without drawing it. But here's my cylinder that is a water tank, and water is leaking out of the cylinder. All right, the radius of the cylinder is 5 meters. All right, and then I have water here. And that's going to be the height of the water, and the height is going down. So the height is changing. But the radius is not changing. Like everywhere there's water in this tank, that radius is going to be 5 meters. All right, so that's important. So let's write down what we're given. So we're given that water leaks out at a rate of 0.2 cubic meters per minute. So when you have a cubic meter, that's talking about volume. So that's the change in volume, dV dt. The water is leaking out, so it's going to be negative. All right, another thing we're given that is a constant is that the radius of this tank is 5 meters. Okay, so what we're going to do is find dH dt when we're finding the height, when the height level or the height of the water is changing, when h is 8 meters. All right, so we're going to write our formula for the volume of a cylinder. So that is pi r squared h. Now at this moment, at this point, if something is a constant, we do need to go ahead and fill it in because it's not changing. So the thing that's the variable that doesn't vary in this equation is the radius. So we would go ahead and we would put 5 in for r because it's not going to change. And so we will do that before we take the derivative. All right. So we're going to plug in constants, values before derivative. Sorry, it's super messy. All right, so now we can find the derivative. So the derivative of v with respect to t, dv dt. All right, 25 pi is just a constant that's being multiplied by the h. So that's going to be 25 pi, and then the derivative of h with respect to time is going to be dH dt. Okay, so this one's a little different. What we want to find is dH dt. So what I'm going to do is take my formula at this point, and I'm going to solve it for dH dt. So to do that, I would divide by 25 pi. All right, I'm going to switch the order if you guys are okay with that. So dH dt should be equal to dV dt divided by 25 pi. All right, so now I'm ready to fill in what I know. All right, dV dt we wrote is negative 0.2 cubic meters per minute. All right, and then we're just going to divide that by 25 pi. All right, there's nowhere to put our 8, and so it's fine. Because that radius was constant, and the rate of change on the height is the same everywhere on this cylinder. So anyway, I typed that in the calculator, and I got negative 0.0025, and this is a change in height. A height is going to be just like a regular meter, a regular inch, and so the change in height is going to be a meter per time, and the time in this problem is minutes. All right, let's get example 3. For example 3, The length of a rectangle is increasing by 3 centimeters per second, and the width is decreasing by 5 centimeters per second. How fast is the area changing at the instant the length is 10 centimeters and the width is 8 centimeters? All right, so we have a pretty good idea of what a rectangle looks like. So I don't think we need a picture. We could draw a rectangle if we wanted to, but let's just write down what we're given. The length is increasing, so that's dl dt by 3 centimeters per second. So increasing is going to be a positive change. All right, and the width is changing by 5 centimeters per second. All right, we're going to find how fast the area is changing, dA dt, when the length is 10 centimeters and the width is 8 centimeters. All right, so let's write our formula. So so because the length and the width are changing, that is going to make a change in the area. So area is length times width. Everything's changing. We don't have any constants. So we'll go ahead and find the derivative. Now on this one, I am going to have to do the product rule. So I'll leave L alone, multiply by the derivative of W, plus leave W alone, multiply by the derivative of the length. Okay, and we want to find dA dt, so that's what it's already solved for. So we're ready to go ahead and just plug in. All right, L is going to be 10, dW dt is 5, W is 8, dL dt is 3. Oh, hold on a second. The width is decreasing, so be careful. I got distracted for a second and I didn't have that. So decreasing, that dW dt is going to be -5. Just like on this one, when water was leaking out, we made that a negative rate of change. I should have done that on this one too, beginning. Okay, so we'll just go ahead and do that multiplication and addition, and we're going to get -26 square centimeters per second. And because it's a change in area, we do a square unit per time. Okay, one more. For example, 4, air is leaking out of a spherical balloon at a rate of 5 cubic centimeters per minute. Determine the rate at which the radius of the balloon is changing when the diameter of the balloon is 20 centimeters. Okay, so we have this spherical balloon. It's not a great one, but we have the parts of a sphere are just the radius. All right, so let's write what we're given. We're given air is leaking out, and then the rate is cubic centimeters per minute, so it's definitely a volume of air. Leaking out is going to be negative. We're going to find how the radius is changing, dr dt, when the diameter is 20 centimeters. Now, the only formula I can think of that uses diameter is the circumference formula, but there's also a circumference formula that uses radius. So that diameter is really not super helpful. So we're going to say when the diameter is 20 or when the radius is 10. All right, so we're talking about the volume of a sphere. So that's V equals 4/3 pi r cubed. Now, it's possible as we go through these problems, you may have to look up some formulas. So just use Google, you're fine. All right, so everything is changing here. The radius and the volume are changing, so I don't have any constants to plug in. So I will take the derivative with respect to time. All right, now I want to find dr dt, so I'm going to take that formula the way it is now and solve it for dr dt by dividing by 4 pi r squared. All right, and I'll switch the order around. So dr dt is going to equal dv dt divided by 4 pi r squared. All right, and according to what we've written, dv dt is -5, and r is 10. Okay, now I am fine with you guys just leaving this as -5 over 400 pi. I would want you to give me the unit. So this is a change in the radius, so it's going to be in centimeters per minute. Now, if you just really, really, really want to type it in the calculator, be careful, because when you divide by 400 pi, you are going to have to put the 400 pi in parentheses, or the calculator will multiply by the pi instead of divide by it. So either one of those is fine with me. I probably would leave it in fraction form. All right. Beginning of related rates.